So here's a Zoom meeting for Physics 231C. This week we're studying actually two chapters, Chapter 11 and Chapter 12. Chapter 11 is on sound mostly, waves and sound. So let's take a quick look at Chapter 11. The first section is on the properties of waves. A function describing a wave might have this form: a cosine kx minus omega t. That's a wave traveling in the x direction. K is called the wave number, and it's related to the wavelength. The wavelength is 2 pi over k. Omega is called the angular frequency. It's related to the period of oscillation. Period of oscillation is 2 pi divided by omega. Frequency is just 1 over t. So that's omega over 2 pi. Angular frequency is 2 pi times frequency. And the velocity of this wave would be v equals wavelength times frequency. Or, in terms of these parameters, k and omega, it's omega divided by k. All right, so that's the mathematics that describes a wave. Oh, this parameter a is the amplitude of the wave. Cosine oscillates between +1 and -1. The quantity f, which is a physical wave, will oscillate between +a and -a. And the wave oscillates in both position and time in such a way that the wave moves in the direction of, in this case, the x-axis. Section 2 is on interference. When you have two waves, they add together. So you add these two functions. Now, because the cosine is an oscillating function, can be positive, can be negative. When you add two functions like that, you may get cancellation. That's destructive interference. Or you may get addition. You may get an increased amplitude. That's constructive interference. Standing waves are waves that the position of the nodes are always constant. So this describes a traveling wave, but if you have a superposition of traveling waves where you add the waves, you can have cancellation. If the frequencies are equal, you can have a cancellation, and then you have waves that don't move in space. They just are fixed in space. They're oscillating in time, but they have fixed positions of the nodes. So, for example, waves on a string where the ends of the string are tied down. Section 3 is on sound waves. Now, sound waves are longitudinal waves in a fluid or a solid, in a material of some kind. The atoms or molecules that make up the fluid are oscillating forward and backward along the direction of the wave. So that makes it a longitudinal wave. Now, an important property of a sound wave is its intensity. How loud is it? Intensity is a physical definition. It's the power per unit area, because a wave will transport energy. So at any particular point, there'll be energy passing by that point. The amount of energy passing a point in a particular through a particular area is the intensity times the area. That's the power. Now remember, the units of power are energy per unit time. So power is measured in watts. A watt is a joule per second. And area is measured in meters squared. So the unit of intensity is watts. That's power per unit. What power per unit area? So that's watts per meter squared. So that would be the unit of intensity. The total power emitted by a source of sound will be the intensity times the total area. The total power. So the total power, P, will be intensity, that's watts per meter squared, times area, that's meters squared. So the total power would be measured in watts. We'll see an example in a minute. Now, intensities vary by many powers of 10, so it's more convenient to express intensities in terms of what's called sound level. The sound level, which is measured in decibels. So we use the Greek letter beta for sound level. It's given by 10 times the logarithm of the intensity over some standard intensity, I0. I0 is sort of the smallest intensity that a person can hear. So the standard intensity, I0, is, I think it's 10 to the minus 12 watts per square meter. So you take the intensity divided by that standard intensity, take the log, it's the log base 10. That'll give you the number of bells, unit defined by Alexander Graham Bell. No, you have to multiply by 100 to get bells, or you multiply by 10 to get decibels. A decibel is 1/10 of a bell. A bell is given by 100 log I over I0. So a decibel is 10 log I over I0. There's a section on musical instruments. There are ways to make sounds that have particular frequencies. For example, organ pipes. There are different kinds of organ pipes. There can be organ pipes that are closed at one end and open at the other end. There can be organ pipes that are that are open at both ends. At the closed end of an organ pipe, there'll be a pressure node. The pressure will be 0 there. At the open end of an organ pipe, that's where the oscillations of the molecules are the largest. That'll be a pressure antinode, where pressure changes are the largest. And so that gives you a way of relating the length of the organ pipe to the wavelength of the sound. There'll be a resonant wavelength and then some overtones. Or there can be stringed instruments where you have a string under tension. So here's the velocity of the wave in a string. It's the square root of the tension divided by the mass per unit length. And you can have a fundamental frequency, which is 2 times the length of the string. The string will be tied down at both ends, so it'll be under tension. So both ends are pressure or are displacement nodes. They're nodes where the motion of the string is, the perpendicular motion of the string is zero because it's tied down at both ends. And so the wavelength will be 2 times, the fundamental wavelength will be 2 times the length. And then there'll be overtones, which are at higher frequencies or smaller wavelengths. Frequency times wavelength is the speed of sound. Or for stringed instruments, that's a constant value, the square root of T over mu. So wavelength and frequency are inversely proportional to each other. Then finally, section 5 is on the Doppler effect. Everybody's heard the Doppler effect when you're standing on the street and a police car sounding its siren goes past you. As it comes towards you, there's a higher frequency. As it goes away from you, there's a lower frequency. Frequency is related to what we call pitch. So high frequency is high pitched, low frequency is low pitched. And, there's a formula for the relationship between the observed frequency, so that's F prime, the emitted frequency, so that's F, the speed of sound, so that's C, and the speed of the source. So these are the equations where either the source is approaching the observer, that's, you're standing on this sidewalk, the police car is coming towards you. F prime, that's the frequency you hear. F is the frequency emitted by the siren. F prime, this number will always be greater than 1. So F prime is greater than F. It's at a higher frequency, higher pitch. On the other hand, as the police car goes away from you, source receding from the observer, F prime is F times C over C plus the velocity of the source. So this is the speed. So V source is the speed. So it's always positive. All right, so that's a quick overview of chapter 11. Now let's look at some problems from the homework assignment. These are mostly taken from the end of the chapter. Consider a doubling of sound intensity. What's the increase in the sound level in decibels? So sound intensity is power per unit area. Sound level is, well, we can write it in terms of the log. It's 10 times the log of I over I0, where I0 is a standard value. I0, I think, is 10 to the minus 12. Now, we want to consider 2 intensities, I1, and then the doubling of the intensity, so I2. So I2 is 2 times I1. I1 corresponds to a certain energy transport. I2 is twice as large. Then what's the difference of the sound level? Beta 2 minus beta 1. So since I2 is larger than I1, the level will be larger than the beta 1. So beta 2 minus beta 1 will be positive, be higher number of decibels. So we take the equation 10 log I2 over I0 minus log I1 over I0. Now think back to college algebra. The log of A minus the log of B is equal to the log of A divided by B. So I can write this as 10 times the log I2 over I0, that's A, divided by I1 over I0, that's B. You see, I2 cancels out. I2 over I1 is just 2. So the answer will be 10 times the log of 2. It's a log base 10. I think the log base 10 of 2 is about 0.3 multiplied by 10. So that'll be about 3 decibels. Here's another problem from chapter 11. Move away from a sound source from distance R1 to distance R2. And suppose R2 is 2 times R1. By what factor does the intensity change? And what's the change in the sound level? So as usual in a physics problem, we draw a picture. So here's the source. Here's an outgoing wave crest, a region of maximum pressure. Remember, sound is a pressure wave. Sound is a pressure and density wave. Pressure increases, density increases. So sound, you could call sound a pressure wave. So here's where the pressure is at a large value. That's the crest of the wave. Here's R2. So here's a pressure crest at a distance of R2. So R2 is 2 times R1. Now remember, intensity is power per unit area. And since we only have one source of power, we could write that as the total power over the total area. That would be the surface area of the outgoing wave. The outgoing wave will be a sphere. It'll be a spherical outgoing pressure pulse. So pressure divided by area. And A is the surface area of a sphere. So at distance R, that would be 4 pi r squared, the area of a sphere. I guess determined first by Archimedes. So I2 will be pressure over A2. I1 will be pressure over A1. It's the same, not pressure, power per unit area. Power over A2, power over, it's the same power because it's the same amount of energy flowing away from the source, and energy is conserved. So by energy conservation, I have the same numerators here, but opposite denominators. So I2 over I1 will be A1 divided by A2. Intensity is inversely proportional to the area because the energy spreads out, and the larger the area, the more the energy is spread out, so the smaller the intensity is. So as you move away from a source, the sound gets weaker. The intensity decreases, the sound level decreases. Now R2 is 2 times R1, so I2 is 1/4. A2 is 4 times A1 because A is 4 pi r squared. So if I double R, I increase the area by 4. So A2 will be 4 times A1. A1 over A2 will be 1 over 4. And then for part B, what about decibels? I have the same equation as I had in the previous problem. 10 log I2 over I1. 10 times the log of 1/4. Now remember, the log is negative for numbers less than 1. So beta 2 will be less than beta 1. So that the difference is negative. Here's problem 93. This involves the Doppler effect. Certain animals can use sound for echolocation. They can locate their position by listening to sound that they emit. So echolocation is a is a method of determining, it's like a method of determining position using sound waves. Not all animals are able to do that. Humans aren't able to do that. But for example, bats can use echolocation. A bat emits an ultrasound burst, say frequency F, as it flies towards a cave wall at a speed V. Now, the bat doesn't want to run into the wall, so it has to know where is it. And of course, it's in the dark because inside a cave, it's completely black. So he can't use his eyes, he has to use his ears. A bat has very large and sensitive ears, and the bat can perceive the frequency of the reflected pulse. And by hearing that frequency, the bat will know how fast it's moving towards the wall. And also, by knowing how long the time delay is, the bat can know how close it is to the wall. So using its brain and those senses, it can avoid running into the wall. So it says, assume air at 20 degrees C, there's a corresponding speed of sound, roughly 343 meters per second. We can take that as the speed of sound. There's a certain frequency, it's ultrasound, so it's a very high frequency, 50,000 cycles per second, 50.8 kilohertz. Hertz is the unit for frequency. Hertz is just the same as 1/seconds. It's cycles per second, oscillations per second. Its speed is pretty fast, 7.3 meters per second. That's pretty fast. I don't know if bats can fly that fast, but anyway, we'll take that as the speed of the bat. That's fast, but of course it's much slower than sound. Speed of sound is 343 meters per second. So we always draw a picture. So here's a picture of the problem. There's a wall, there's a bat, the bat's flying towards the wall. The speed of the bat is V. The bat is emitting sound waves. It's got some kind of voice box by which it emits sound waves at this very high frequency. The sound waves will reflect from the wall, and the bat will receive the sound waves that reflected off the wall. So we'll define the frequency F as the frequency emitted by the bat. That's this 50,000 hertz. F1 is the frequency of the wave that hits the wall. Well, why isn't that the same as 50,000 kilohertz? Well, because there's a moving source. So there's a Doppler shift. So the frequency of the waves hitting the wall is C over C minus V times F. Well, that's F1, where C is the speed of sound, and this is the appropriate formula for an observer, that's the wall, and a source moving towards the wall, an approaching source. So you see this number will always be greater than 1. So F1 will always be greater than F. It's like the police car approaching you when you're standing on the sidewalk. We'll take F2 to be the frequency of the wave that hits the bat's ear. Now, why isn't that just the same as F1? Well, because the bat is moving. So here we have another kind of Doppler shift where you have a stationary source, but a moving receiver. Then the Doppler formula is a little different. The Doppler formula is C plus V over C times F1. The waves coming off the wall have the frequency F1. The waves observed by the moving observer is this factor C plus V over C. Now that'll always be a number greater than 1. So F2 will be greater than F1. And the problem is to calculate F2. So the formula for the Doppler effect is kind of complicated. It depends on who's moving. Is the observer moving or is the source moving? Or are they both moving? There are 4 possibilities. I mean, you could have the observer at rest and the source moving toward or away. That's 2 possibilities. You could have the source at rest and the observer moving toward or away. That's 2 more possibilities. So there's also altogether 4 possibilities. And it's always a ratio of speeds. It's C plus or minus V of the observer divided by C plus or minus V of the source. Whether it's a plus sign or a minus sign depends on whether it's approaching or receding. And you can always figure out that the higher frequency is when the 2 are approaching. Okay, so that's echolocation. Here's a problem about waves on a string. So if we have a piano string, it has a certain length. It's tied down at both ends. It has a certain length. It has a certain tension, and it has a certain mass density. And the speed of the wave is the square root of the tension over the mass density. So T is tension. That's a force. So that has units of newtons. Newtons are kilogram meters per second squared. Mu is the mass density. Now, since it's linear, it's the mass per unit length. So that's kilograms per meter. So you can see what the unit is. It's the square root, kilogram meters per second squared divided by kilograms per meter. The kilograms cancel. This meter, this divided by meter in the denominator becomes meter in the numerator. So you have meters squared per second squared under the square root. So that'll be meters per second. So that's the speed of the wave. Now this is actually a standing wave. This is the fundamental frequency. But you could also have traveling waves. You could have a traveling wave on this string. But this is a standing wave where that's the fundamental frequency. The wavelength, this is half a wave. But both ends have to be nodes because the string is tied down. So half a wave is the length of the string. So the wavelength is 2 times the length of the string. Or the frequency is the speed of the wave over the wavelength. This has to do with tuning the string by changing the tension. So before the tuning, you have 1 over 2L. Let's see, let's solve for F. Lambda is 2L. So it's 1 over 2L times the speed of the wave is the square root of T0 over mu. That's the tension before tuning. After tuning, it's 1 over 2L times the square root of T over mu, where it says T is 12 newtons larger. So there's an additional there's an additional 12 newtons applied by the piano tuner. So you have here 2 equations with 2 unknowns. You have to use algebra to solve for the unknown, which is mu. The tension changes, but the mass density doesn't change. So the unknown is mu, but you need several equations to calculate mu. That doesn't really involve sound. Well, the piano string makes sound waves when it oscillates. So we're just calculating the behavior of the string. As the string oscillates with a certain frequency, it stirs up the air Well, actually, no. In a piano, the string causes vibration of the soundboard. And the vibrations of the soundboard stir up the atmosphere and create sound waves. And the frequency of the oscillations of the soundboard will be the same as the frequency of the string. This only shows the fundamental frequency. There are also overtones. All right, so you know, the chapter is about both waves and sound. That's chapter 11. Now there's an exam coming up. There'll be an exam next week. And the exam will include chapters 9, 10, 11, and also 12. So 9 was gravity, 10 was fluids, 11 is sound, 12 is temperature. So don't forget chapter 12. That's also on the homework assignment, which is due Monday. So you should be reading chapter 12. The reading exam for chapter 12 is due today, I think. The problem set is due Monday. It's a kind of a long problem set because it combines 11 and 12. So the problem set's about 1/2 on chapter 11, 1/2 on chapter 12. But there'll be a question about chapter 12 on the exam, maybe 2. So don't forget chapter 12. The topic of chapter 12 is temperature and gases. Temperature is a property of matter. Any sample of matter has a certain temperature. Whether it's a gas, a liquid, or a solid, it'll have a certain temperature. Now, what exactly is temperature? Well, temperature is the thing that equilibrates when different materials are in contact. When different materials are in contact and you leave them in contact for a while, they'll come to the same temperature. Temperature is a measure of their difference in energy content. So there's a relation between temperature and energy, which is simplest in the case of gases. So there's a section in chapter 12 on the kinetic theory of gases. You know, a gas has various observables: pressure, volume, temperature, mass, density, and so on. They can all be related to the kinetic energy of the molecules that make up the gas. So we've studied kinetic energy earlier in the semester. So we know all about kinetic energy. We know a particle has kinetic energy 1/2 mv squared. Well, a gas is made of a bunch of particles, but a large number of particles. Each particle will be moving with some speed, will have some kinetic energy. So the whole sample will have some energy, which is just the sum of the energies of all of the particles that make up the sample. There's an associated pressure. That's the force that the gas exerts on the wall of the container it's in, for example. And pressure is given by N, the number of particles, divided by V, the volume they're enclosed in, because a gas has to be enclosed in a volume or else it'll just all spread out. So N over V, 1/2 mv squared would be the kinetic energy. Now, each particle has a different kinetic energy. So the whole distribution of kinetic energies. So what goes in this formula is, I put it in angular brackets, this is the average of the speed squared. The average velocity is 0 because they're all traveling in different directions, and velocity is a vector. The velocity squared is the square of the speed. That's not a vector. That's just a scalar. It's always positive. The average value of the square of the speed is called the mean square speed. square root of this is the root mean square speed, but the average of v squared, that is to say, the average of, well, speed squared, 1/2 mv squared would be kinetic energy. So that's the average of the kinetic energy, multiplied by 2 actually, is the numerator of the pressure, and the denominator is 3 times the volume. You can check that the units make sense. The numerator has units of joules, same as kinetic energy, 1/2 mv squared. So this is joules divided by volume. Now, volume is meters cubed. So it's meters squared times meters. Now, joule divided by meter, well, joule is the same as the unit of work, and work is Newton meters. So joule divided by meters is newtons. And that's joules divided by meters. And then we have also meters squared. Newton per meter squared, that's the unit of pressure. 1 Pascal is 1 Newton per meter squared. So that's the pressure in a gas related to the kinetic energy of its molecules or atoms that make it up. But what about temperature? Well, here's the relation between temperature and energy. Temperature is not the same as energy. It's different than energy. It has a different unit. The unit of temperature, well, there are several units of temperature. It's degrees. Could be degrees Fahrenheit, could be degrees Celsius, could be Kelvin degrees, whatever you're going to measure it. It doesn't have a unit of energy. Energy is joules. There's a universal constant of nature, which is called the Boltzmann constant, named for the great Ludwig Boltzmann. Who was one of the first physicists, the first scientists who really understood temperature, energy, entropy, thermodynamics. And in his honor, there's this universal constant, K Boltzmann. And 3/2 K Boltzmann times the temperature is the mean square kinetic energy in a gas. A little more complicated in solids and liquids, but gases are the easiest. The mean kinetic energy of the atoms in a gas is 3/2 Boltzmann's constant times T. And Boltzmann constant is a universal constant. It's the same for all materials. It's universal. So you see how simple nature is. Although we have many different kinds of gases, there must be hundreds of different kinds of gases, but they're all described with respect to temperature by the same universal constant, Boltzmann's constant. All right, so that will be the Zoom meeting for today. And there's a exam coming up, so make up your exam help sheet. 1 sheet of paper, 2-sided, with all the equations that you're going to need to do the exam problem.